In the first video lesson, we talked about the concept of a chemical formula and how this could be either an empirical formula, a molecular formula, or a structural formula. And we also started talking about how we name compounds, and we focused on ionic compounds, and we talked about how we name cations and anions. In the second video lesson, we're going to continue to talk about naming. We have to know how to name things, but here we will focus on naming molecular compounds. What do we mean by a molecular compound? Well, we mean a compound that is formed primarily by covalent bonds, which, we'll get to bonding and the different kinds of bonds, but primarily by covalent bonds. And molecular compounds can be binary compounds. Many are binary compounds. By a binary compound, we mean a compound, a molecule, made by joining two different elements, different amounts of two different elements, like H2O, two hydrogens, one oxygen, but only two elements, hydrogen and oxygen, so it's binary. Now, the simplest binary compounds are what we call homodiatomic elements, like H2, diatomic hydrogen, or hydrogen, nitrogen, which is N2, oxygen, O2, fluorine, F2, etc. Now, these are actually the elemental forms of these elements. They exist in nature as homodiatomic elements. But we can form a large number of other compounds by bonding nitrogen to hydrogen, nitrogen to oxygen, nitrogen to fluorine, etc. When we name a binary compound, we do not change the name of the first element that will appear in the molecular formula of the molecule. We'll get to that in a second. But the second element, we add an IDE to the ending. And we use the prefixes di, tri, tetra, penta, hexa for, of course, 2, 3, 4, 5, 6 to indicate the number of the atoms of an element in a compound. Note that we do not use the term mono, or we don't use it very often, but we tend not to use mono if there's only a single. For example, NO2. If the molecular formula for a compound is NO2, its name would be nitrogen dioxide. Again, we name the first element that we see as its given name, and then we use the prefixes when necessary, and we change the ending of the last element to have an IDE. So nitrogen dioxide. In my second example, it would be dinitrogen tetrafluoride. So notice we use di to indicate two nitrogens, tetra to indicate four fluorides or four fluorines, but we change the ending of fluorine to "ide" because it's the second place in the name of the molecule. So these are the rules, not very difficult, for naming molecular compounds, especially those that involve only two different elements, what we call binary compounds. Later on, we'll talk about much more complicated molecules in the organic chemistry and more complicated naming systems, but this will get us through a great deal of general chemistry. Now, there are a large number of compounds that have common names. H2O. Really, we don't call this dihydrogen oxide. We call it water. NH3. We don't call it nitrogen tetrahydride. People might not know what we're talking about. Instead, we call it ammonia. N2H4, again, could be called dinitrogen tetrahydride, but instead we have a common name, hydrazine. And of course, C6H6, the common name is benzene. And there are many other compounds that have common names such as this. But most of the time we will use the above naming system. And if you happen to call H2O dihydrogen oxide, well, that's really gauche. We'll just try to coach you as to not to do that. Okay? Now, how about acids? In the last lecture, we talked about anions, and if you look at the left column of this chart, you'll see anions that end in IDE, such as chloride, ate, such as nitrate, perate, such as perchlorate, ite, such as nitrite, and hypoite, such as NO-1. If we add one or more hydrogen ions to make this now a neutral molecule, how do we name that neutral molecule? Well, first of all, that neutral molecule will be an acid in these cases. How do we name it? Well, an ide, like chloride, becomes a hydro ic acid, where that refers to the particular element that we're talking about. So in the case of chloride, it will become hydrochlor, for chlorine, chloric acid, hydrochloric acid, which you've all heard of this name before. And 8, if the anion is an 8, such as nitrate or carbonate or phosphate, it becomes a ic acid. That is the name pertinent to the anion, and then add ic acid. So nitrate becomes nitric acid. Similarly, a per 8 acid, such as perchlorate, becomes a per ic acid, such as perchloric acid. An ite acid, such as nitrite, becomes an us acid. So nitrite will become nitrous acid. And a hypoite, such as NO-1, becomes a hypous acid, such as hypochlorous acid. As with any set of rules for naming, it'll take you a while to go through and review these rules in practice, and you'll see that they're not so bad. Two in particular to make sure that you don't confuse. Hydrochloric acid is HCl. Chloric acid would be HClO3. Remember, if you look at the second row, chlorate would be an 8. It becomes an ic acid, so HClO3 would be chloric acid. So if you can keep straight hydrochloric acid and chloric acid, those are two of the more difficult ones. Then it's all downhill. Look at the bottom, I say that HF is one that we have to pay attention to. There are a few others, but in particular HF. Because HF, if it has a little parentheses with a G behind it, that means HF is in the gaseous state. When HF is in a gaseous form, we consider it a binary molecular compound, and we name it as we did in the previous slide, and we call it hydrogen fluoride. If HF has a little AQ, that means it's dissolved in water and it is acting as an acid, and then we name it as an acid, and this would be then hydrofluoric acid. Naming acids is a little challenging, I'll give you that. Naming bases is fairly simple. And in fact, we will deal mostly with just a few bases. Sodium hydroxide. And sodium hydroxide is named just as you might imagine by naming an ionic compound. We name the sodium cation and then the anion, which in this case is hydroxide, sodium hydroxide. And we'll also deal with potassium hydroxide, calcium hydroxide, etc. Another base that we will deal with occasionally is ammonia, this molecule with a common name which we had on the previous slide. Okay, so that was about naming and rules for naming. Now let's talk about a very important concept that we will use this concept from this point on. And that is the fact that in a chemical reaction, such as I've shown in this slide, where we have reactants on the left going to products on the right with an arrow telling us which way we're going towards the products. We have two hydrogens, happen to be in a gas phase, plus an oxygen, happens to be in a gas phase, going to two water molecules. Okay? Now, what we mean by such a reaction is that two molecules of hydrogen gas react with one molecule of oxygen gas to form two molecules of water. That's if we were able to look just at the molecular, just at one or two molecules at a time. But again, in practical terms, we don't deal with molecules. We deal with a larger scale that we can measure ourselves, and that means that we deal with what is called the mole scale. So we can also say that 2 moles of hydrogen gas react with 1 mole of oxygen gas to form 2 moles of water. Okay, so we scale up. We scale up for practical reasons because we can't easily handle molecules or atoms, but we can handle mass on the scale of grams. So we must be able to convert between moles and mass, and of course we do this with the equation shown at the bottom, where we have the number of moles is equal to the mass divided by the molar mass, or what we oftentimes call the molecular weight, which we will abbreviate as MW. So the molecular weight of water is 18 grams per mole. If we have 18 grams of water divided by 18, we have 1 mole. If we have 36 grams of water, we have 2 moles. 54 grams, 3 moles, etc. So this is our relationship, and I'm sure you knew it already, how we convert between mass which we can weigh out, and moles of a substance. And we will use this in just about every equation that we use from this point on, converting between mass and moles. And this conversion might go the other direction. If we know how many moles we have, we can convert that to mass by multiplying by the molecular weight. Now let's talk a little bit about percent composition. We tend to write the molecular formula as something like NH3, one atom of nitrogen bonded to 3 atoms of hydrogen. But we could also express the composition of a molecule in terms of the percent composition by mass of each of the components. Now it turns out it's a little more cumbersome, but you'll see why we sometimes have to do this. Let's take as an example the molecule CF4, carbon tetrafluoride. And let's ask the question, for carbon tetrafluoride, what is the mass percentage of that molecule that would be carbon? Okay, how do we do that? Well, if we had 1 mole of carbon tetrafluoride, it would contain 12 grams, or 1 mole, 12 grams of carbon. And then if we divide that by the total molar mass, which would be the mass of 12 for carbon plus 4 times the mass of 19 for fluorine, we would, and then multiply by 100% to convert it to a percentage, we would see that carbon tetrafluoride is 13.64% by mass carbon. And of course, the rest of it, the 86.36%, must be fluorine. So if we were to call up a friend of ours or text a friend of ours and say, I've got this molecule, it's 13.64% carbon and 86.36% fluorine by mass, we could do that. It might be a little confusing to whoever is receiving this message, but we could certainly do that. Well, what if somebody does tell us the mass percentage of 2 different elements like carbon and fluorine that they have in a sample, and then we want to convert that to a molecular formula? How do we proceed? And of course, this is the way that you will most often have to do the problem. If you're given a mass percentage of 2 or more elements in a compound, the best advice is to start by assuming that you have a convenient sample size, such as 100 grams. Could be 1,000, but let's say 100 grams. So that if you're told, for example, that a substance is 13.64% carbon, and 100 grams, that would be 13.64 grams of carbon. And if the rest of it is fluorine, 86.36% is fluorine, then in a 100 gram sample, that means that 86.36 grams is fluorine. So in that representative 100 gram sample, that would be the mass. 13.64 grams would be carbon, 86.36 grams would be fluorine. Okay, just simple logic. If you then divide each of these masses by the molar mass of those elements, that is, divide the 13.64 grams by 12 grams per mole, you get the number of moles of carbon in that 100 gram sample. Likewise for fluorine, you get the number of moles of fluorine in that sample. Those values are shown, 1.137 moles of carbon, 4.545 moles of fluorine. That would be the mole-to-mole ratio of carbon to fluorine in that representative sample. Now, here's a general strategy that we'll use several times. If you then divide these 2 numbers of moles, the moles of carbon and moles of fluorine, by the smallest number, you would then get the ratio of the number of moles of fluorine to carbon in the molecule. So dividing by the smallest number, you get a relative number of 1 for carbon and 4 for fluorine. So for every 1 carbon, there is 4 fluorines. So you would be able to determine the molecular formula given the percent mass composition in that molecule. It's cumbersome, but you could do it. Now, why might you want to do this? Well, that's because maybe sometimes in an experiment, you don't know the molecular formula, but you do some kind of analysis, such as a combustion analysis, which we'll talk about in the next video lesson, which provides for you the percent mass composition so that you can then determine the molecular formula. So that's what we'll go into in the next video lesson.